Hey everyone! In this introductory lesson on waves, we'll be getting into some of the basics of waves. What are waves? What are some of the defining parameters of waves? And what are the relationships among those different parameters? So let's dive in. All right, so first of all, in terms of what a wave is, you may have already seen this video seeing a stadium wave at this game here. So if you watch the stadium, not the players, you can see the wave moving on through. That's a good one. All right. So that's good. All right. So what we're seeing is this wave moving through the stadium, which is a reflection of the motion of these people in the stands, the motion of these spectators. Now, what I want you to notice, though, is that we see the wave moving to the left across our screen. So it's moving horizontally, but each individual person in that wave, they're not moving horizontally, they're moving up and down when it's their turn to be part of the wave, essentially. So what we see there is that the movement of the wave, it's not the movement of any one person. It's not the movement of an object. What a wave is describing is this movement of energy. We see this spike in energy passing through the stands, and that is what we then interpret as a wave. So a wave is a disturbance that transfers energy, not objects, not matter, okay? And so when we look at a wave and we identify a wave moving through something, typically for most waves, for mechanical waves, a wave has to be traveling through something. We call that the medium, the material that our wave is traveling through, right? So some of those basic characteristics, basic defining features of a wave. Now let's get into a little bit of wave anatomy, all right? So here we have a picture of a couple waves superimposed on each other. You may notice that the slinky is showing a longitudinal wave, where we're sort of creating a disturbance in the same direction that the wave is traveling. And then in the lime green, we see the sine wave, which represents a transverse wave, where this disturbance is perpendicular to the direction of wave travel, okay? But regardless of which type of wave we're talking about, there are a couple key parameters for us to be familiar with in terms of defining this wave, all right? So I'm gonna focus in on that lime green sinusoidal transverse wave here because it's a little bit easier to see what's going on in 2 dimensions, all right? So one key parameter, one key component of this anatomy is what we call the amplitude of the wave. So we see that that's essentially like the height of the wave. If we're thinking about our stadium wave, the amplitude would essentially be like, how high are the people standing up? Are they just doing a little like just barely out of their seat, or are they doing like a full-on stand and jump? That would be sort of a measure of the amplitude. How big of a disturbance are we seeing there? And then along our other dimension, our other key parameter is wavelength, all right? And so wavelength then is describing how long the wave is, all right? The distance from peak to peak or trough to trough. If we're thinking about our stadium wave, wavelength is essentially a reflection of like how many people are all standing at the same time. How wide across is that wave going to be, okay? So that's a little visual to help you out, but let's go ahead and put some of these ideas into words as well, all right? So again, we saw amplitude, which we would represent in terms of variables as just a capital A for amplitude, all right? Amplitude is describing the displacement of the individual particles in the medium while the wave is passing through, all right? So it describes the maximum displacement from the particle's rest position. In other words, how far out of their normal position are our particles moving when the wave passes through. Okay, and that's a spatial parameter, so that would be measured in meters. Our other spatial parameter, as we saw previously, is wavelength. Now, the variable to represent wavelength is a Greek letter lambda, which you can see right there. To me, I kind of think of it as like, it's sort of like a candy cane that's falling over, and then there's a little leg to hold it up, okay? So like a little arch there, and then one more just straight line coming off of it, okay? So that's our wavelength, and again, that describes how long the wave is, the distance that our wave travels during the course of one cycle, okay? So the measurement of like peak to peak or trough to trough, something like that, okay? So that's another spatial parameter measured in meters. technically, really, when we talk about wavelength, we're really looking at like meters per wave. How many meters does the wave travel per wave cycle? But we often just sort of abbreviate that and just think of it in terms of meters. Either way of thinking about wavelength units is fine, okay? Now, there are a couple other wave parameters for us to be familiar with, which are not spatial in nature, but more temporal, more related to time, okay? One of those is period, which in terms of the variable we use to represent it, that's a capital T, because it's a special measurement of time. It's the amount of time it takes for a wave to complete one full cycle, okay? The time it takes for it to reach a peak, and then stop, and then reach a peak again, okay? So that's going to be measured in seconds, or again, really that's seconds per wave, but we can kind of just think of it as seconds, and that works fine, okay? So periods describing the amount of time it takes to do one full wave cycle, and then sort of the flip of that is frequency, represented by a lowercase f, all right? So frequency describes the number of wave cycles completed per second, all right? Or in other words, if we're thinking about like a slinky wave, for example here, frequency would be like, how many times do I have to move my hand per second as I'm moving this wave down the slinky, okay? So the number of disturbances there per second, the number of waves per second, okay? We have a special unit to measure frequency, and that is the hertz, which we abbreviate with a capital H lowercase z. And basically 1 hertz describes 1 wave per second, okay? So cycles per second are our units for frequency, which we abbreviate to just be hertz. All right. So those are some of the different features of wave anatomy then. And the anatomy of a wave then dictates how we perceive that wave. So we're going to focus in on light waves specifically. We could talk about sound as well, but for the sake of simplicity, we're going to keep sticking with light so that we can get ready to talk about stars later. Woo-hoo. All right. So let's start by considering these 2 light waves. So quick check for understanding, what is different about these 2 light waves that you see represented on your screen right now? What I see is they're the same length across, right? But the height of those waves is different, which means that they have different amplitudes. The one on the left has a high amplitude because it's a taller wave, a bigger disturbance for our particles, and then the one on the right is a lower amplitude, less of a disturbance there, okay? Let's take a guess as to what would that look like. How would a high amplitude light wave look different from a low amplitude light wave? So we interpret amplitude as brightness, all right? So that's how we perceive the amplitude of light waves. Higher amplitude light waves look brighter to us. Lower amplitude light waves look dimmer to us. So brightness is a function of the amplitude of those light waves. Okay, let's consider another pair of light waves here over on the right. Take a moment to identify what's different about these 2 light waves. So we could think about those differences in a couple different terms here. What I'm seeing is that the one on the left is more like accordion scrunched, and then the one on the right is more spread out, farther apart, wider here, okay? And so that basically gets at a difference in 2 things. It's a difference in frequency, and it's a difference in wavelength. So I can see that the first of those 2 waves has a higher frequency. It's oscillating more times per second, and it also has a shorter wavelength because it's more squished inward, all right? Whereas the one on the right, I can see it's a lower frequency. It has fewer disturbances per second and also a longer wavelength. It's more spread out, all right? So let's take a moment to try to predict, how is that going to affect our interpretation, our perception of these light waves? How are these 2 waves going to look different to us if they are light waves? So the frequency and, as a result, the wavelength of light affects the color that we see, assuming that this light wave is in the visible range, okay? So if we're talking about visible light, higher frequency, shorter wavelength light waves look bluer to us. As we decrease the frequency, as we spread out, make those waves longer, they get redder and redder, all right? So they go from like blue to green to yellow to red, okay? Now again, I've specified that's only if we're staying within the visible range. If you take a red wave and you continue to stretch it out farther and farther and farther, you end up with a wave that we're not able to see, but it's still ultimately a light wave. It's just outside of the visible range. Okay? So this brings us to the idea of the electromagnetic spectrum. All right. So it turns out that there's a ton of light that's going on, that's radiating all around us all the time, that we are just not able to see. Our eyes are incapable of perceiving these other frequencies of light waves, but those waves still exist. All right. So when I use the term radiation, or when I use the term light, I actually mean something much more expansive than just that little range of like Roy G. Biv that we are able to see. Okay. So we can see visible light sort of here in the center of that electromagnetic spectrum here. Okay, but if we were to continue stretching out those waves, make them longer, make them less frequent, we get down into the infrared range. All right, so we can see then this other, or we can't see, literally we cannot see infrared light waves, but they're still light waves, just longer. That's all they are, okay? If we keep stretching them out, we get down to microwaves, like the things in your microwave oven that cause your food to get hot, right? And then if we keep stretching them out farther and farther and farther, we end up with radio waves, which is how you're able to hear radio, all right? So radio waves and visible light, same thing, just different wavelengths, okay? That's really the only difference between them, right? Now, if instead I were to take blue light and I were to continue to compress it and scrunch it in and increase the frequency further, I get up into UV, or ultraviolet light, okay? If I keep scrunching it, it becomes X-ray light, and then ultimately if I keep scrunching it, now we're getting into gamma rays, which are generally not great for us, as it turns out. So as we increase the frequency of light, it's higher energy and it becomes ionizing. It can kind of mess with the molecules in our DNA and cause mutations, cancer, badness in general. All right, which is why we tend to try to avoid exposure to gamma radiation, to X-rays. Even UV from the sun causes skin cancer, because if we get into that higher end of the UV spectrum, that gets ionizing as well. But you could stare at a visible light all day and, you know, your eyes would hurt. It wouldn't be great for them, but you're not going to get cancer from visible light per se, right? So just to give you a little picture of, like, when we talk about light and we think about just visible light, that's just a little teeny piece of the pie. There's tons of other types of light that are traveling around us all the time that we're just not able to see, as it turns out. So kind of fun there. Okay, so so that's our electromagnetic spectrum, and a picture of kind of all these different types of light here. Now, let's get a little bit more into then some of these relationships among these different parameters here, okay? So I asked you in your investigation to gather some data on frequency of a wave and period of a wave and see what relationship there was between the two of them. What relationship did you identify between frequency and period? Should have found an inverse relationship, that as you double the frequency, the period drops in half. So whatever factor one multiplies by, the other divides by that same factor. And this is actually because frequency and period are reciprocals of each other, all right? They're really the same exact thing, just flipped upside down, because period is seconds per wave, frequency is waves per second. All right, so same thing, just flipping it upside down. So period is equal to 1 over frequency, or you could think of it as frequency is equal to 1 over period. They're just reciprocals of each other, okay? So let's take a moment to kind of use that. So say we've got a kid on a little rope swing, swinging down from a tree branch, okay? So they swing down, they don't let go because they're too freaked out. So then they come back and they like whack their head on the tree branch. Ouch. All right. And that just sort of keeps happening over and over, this poor, dazed, battered child. All right. So it goes back and forth a bunch of times. Ultimately, over the course of 10 seconds, the kid goes out and hits the tree branch 5 times. Okay. So let's take a moment to analyze this child's suffering. What is the period of that swinging, and what is the frequency of the swinging? All right. So now, to figure out what the period is, that's the amount of time it would take to complete one full wave cycle, okay? So one experience of going out and coming back again, okay? So if I consider that in 10 seconds, we had 5 wave cycles, ultimately I can just set up equal proportions to figure out the amount of time it took to do one full wave cycle, right? So the period per one cycle is equal to this 10 seconds over 5 cycles, which means that the period of a single swing is 2 seconds. Total of 2 seconds to go out and back again, all right? So now that we know that the period is 2 seconds, what is the frequency of the child swinging? So to figure out frequency, all I have to do is take the reciprocal of the period. So that's going to be 1 over 2 seconds, or in other words, 0.5 hertz is the frequency of this child's hurting. That's appropriate. All right, anyway. So that's our relationship for period and frequency. Let's dive into one more relationship as well, which is frequency and wavelength. So what relationship did you find between frequency and wavelength? Still an inverse relationship, okay? So if we double the frequency, the wavelength drops in half, as does the period, okay? So still an inverse relationship between both frequency and wavelength. Now you should have noticed something kind of interesting. If you multiplied frequency by wavelength, what do you end up with? All right, so frequency is gonna be waves per second. Wavelength is meters per wave. So if I multiply those two together, the wave piece kind of cancels out, and I'm left with a unit of meters per second. We've seen that before. That's speed. That describes the speed at which the wave is traveling through the medium. So frequency times wavelength is equal to the speed of the wave, how fast it's traveling through its environment, okay? And we'll put that into equation form in just a moment. But first, I really quickly want to address that. Does this mean that changing frequency changes the wave speed? It does not. What we should find is that if our frequency goes up, the wavelength automatically goes down. So they still ultimately multiply to the same wave speed. Those two changes cancel each other out. The wave speed is unaffected by changing the frequency of our wave. All right. So again, frequency times wavelength, though, does give us wave speed, which brings us to these two equations. They're the same thing, just rearranged, right? So wavelength is equal to speed of the wave divided by frequency. So we're seeing that inverse relationship. Or if people don't like having fractions in their equations, we've got that wave speed is equal to frequency times wavelength. Okay, so wave speed in meters per second equals frequency in hertz times wavelength in meters. Okay, so let's use that for a moment, okay? So speed of light through a vacuum is about 3 times 10 to the 8th meters per second, about 300 million meters per second. It's kind of fast, all right? So a green light wave has a frequency of about, we're solving for the frequency of our green light wave. Typically, green light waves are about 5.1 times 10 to the negative 7 meters long, so we want to figure out what the frequency of that wave is, how many cycles it is completing per second. So I'll go ahead and use my guess method. So the information given to me is I know the speed of light is 3 times 10 to the 8th meters per second, and I know that the wave is 5.1 times 10 to the negative 7 meters long, so that's the wavelength, because that's how long the wave is, all right? And we're solving for frequency, okay? To relate those together, I'm going to use my wave speed equation. So speed equals frequency times wavelength. If I want to solve for frequency, I'm going to divide both sides of that equation by wavelength, which gives me that frequency equals speed over wavelength. So then I'll go ahead and plug those things in, being sure to put parentheses around my entire denominator so that everything stays there in the denominator and nothing sneaks back up to the numerator, okay? And when I do that, I determine that the frequency of a green light wave is about 5.9 times 10 to the 14 hertz, okay? So 5, 9, and then 13 zeros after that. That's a lot of waves per second, all right? Light waves, high frequency on that one. So then let's take a moment to figure out what are the factors that determine the speed of a wave. What dictates how fast a wave moves through a space? Now, what we should have found is that wave speed is independent of all of those different features of anatomy that we've talked about previously, okay? So amplitude doesn't change wave speed. Frequency, period, wavelength, none of those things changes the speed of the wave. So the wave anatomy has no influence on how fast that wave is able to move. So then the question becomes, what does influence how fast a wave is able to move through a space? What it comes down to is the wave speed isn't dictated by the wave itself. It's dictated by its environment, by the medium that our wave is traveling through. Okay, so ultimately the wave will go as fast as it can go, subject to the limitations of the environment that it's trying to pass through. Okay, so some of those different characteristics of the medium that can play a role in this would include composition, so what is the material made of, the density of our medium, the temperature of our medium, how fast those molecules are moving, and the state of matter, among other things as well, right? But ultimately, the environment is what dictates how fast our wave is able to move, but changing the frequency, period, wavelength, amplitude, none of the features of the wave itself dictate how fast it's going to move. It's all about the environment, okay? So let's take a moment to do a little check for understanding. So here we've got light waves from two different flashlights, A and B, all right? So let's take a moment, figure out which flashlight is brighter. Flashlight B is our brighter flashlight because those light waves have a higher amplitude. They're taller, therefore we perceive them as being brighter. Secondly, one of our flashlights is emitting red light and the other is emitting green light. Which is which? Flashlight A is producing our red light, flashlight B is the green light, and that's a function of the wavelength. So longer waves mean redder waves if we're in the visible spectrum, and then as we compress and make those waves shorter, they get yellow, then green, then blue. Okay, so since flashlight B has the shorter wavelength, it must be the green light. Last question, which of these flashlights is producing light that's going to move faster through the air? Neither. They're both going to move at the same speed through the air because, again, the color of the light, the brightness of the light, none of those things influences the speed. It's all just a function of the air that our light is traveling through. All right? So there's your introduction to waves. Hope that clarifies some things. Let me know what questions you have. Good luck.